So we're going to spend, this is like 60 slides, so this is a long presentation. It's just an overview of all kinds of earth retention systems, so we'll take a break somewhere in the middle of it. Pretty simple, straightforward stuff. There are a bunch of different classification systems for earth retention systems, and like lots of classification systems, you need something to start you off to try and put this huge world of earth retention systems in some kind of cubbyhole so you have some understanding of how different systems behave and how they're designed, but no matter how you slice the pie, it doesn't work all the time. And this one is taken, this is after one of those summary papers by O'Rourke and Jones. I think it's one I'm going to have you read. But it's reprinted in the FHWA manual that we talked about. And so this is a pretty common way to discuss earth retention systems. And that is, the initial division is about whether the systems are externally stabilized versus internally stabilized. And most earth retention systems we use are externally stabilized, which means we are either constructing some structural system or installing a structural system in the ground that supports the soil outside of the soil itself. So if you think the classic one is a cantilevered retaining wall, we're going to build a structure that's basically two concrete beams, one vertically oriented, one horizontally oriented, and then we're going to put soil behind it. And it's that structure which is external to the soil, and that gets a little confusing sometimes because the footing's below the ground and it's in the soil. But really the structure itself is external to the soil behind the wall, the retained soil behind. So that's a classic externally stabilized system. A classic internally stabilized system, which is very popular now, is mechanically stabilized earth. Well, we're actually building reinforced soil. We're putting reinforcing soil elements within the soil that's being retained, and that soil is acting like a reinforced material. So that's the distinction between externally and internally stabilized. But then another really important distinction is whether the systems are for cut walls or fill walls. And so that the classic difference there is if we've got some slope here and we want to create some open space down here because we're going to build a house or build a road or something, that would be an example of a cut wall where we're going to come in and do some temporary excavation here. We're going to come in here and build some kind of a structure, and then we're going to fill it back up. Or in the case, if this was the ground surface and I want to create, maybe this is the original ground surface like this, and I want to fill this area in here, we're going to come in and we're going to build some kind of wall in here and we're going to fill behind it. So those are both fill systems in the sense that in this one I cut in a temporary cut in order to build it and then filled it. So those are both fill systems. A cut system would look like this in the first case, where instead of doing this temporary excavation, I'm going to come somehow in here and I'm going to install the wall either before I start cutting over here or as I cut, I will be installing the wall. So that's what we call a cut wall versus a fill wall. So it doesn't really have to do whether the section is a cut, because this is a cut section in both cases. It has to do with how the wall is constructed. If I do a temporary excavation and cut the wall back, as I did in the red case there, and then build a wall and fill behind it, it's a fill wall. The cross section is still a cut section. If this is your road, it's being a cut section. But the wall is not a cut wall because I built the wall and then filled behind it. If I'm doing this sort of top-down construction, and timber lagging walls are a classic one, and most earth retention systems for temporary excavations are cut walls, it's the way the wall is installed. It's a question of whether the wall is installed before the filling behind it, or whether it's installed during the actual cutting operations. If you're in a situation where you have a fill place like that, then all the walls are fill walls. You don't put a cut wall in a place where the actual elevation is a fill elevation. So those are some ways we can divide walls, and this is really just sort of a reiteration of that previous slide, but I think it helps a little bit. So in this one, I'm doing the primary difference between whether we're talking about fill walls or cut walls. Same information presented in a different way. So in the fill wall category, one of the first categories is rigid gravity walls or semi-gravity walls. So these are walls that are using gravity basically to maintain the stability of the wall itself. And so if you've done any kind of cantilever retaining wall design, you got to worry about sliding and overturning. And the way we do that design is we make sure that to make it simple, that the heel of the wall is big enough that there's enough gravity behind the heel to hold the wall in place. And you need to worry about the structure of the wall. The older version of that is just a concrete gravity wall that doesn't have the cantilever feature, and I'll show you a gravity wall where it's just the mass of the wall itself that is providing both the earth retention and the structural support for the wall. Those are pretty unusual these days. There are a bunch of prefab modular systems. We're going to cover all these, and the common ones are crib walls, bin walls, and gabions, but it's where the material that's built up the wall is actually prefab sort of material. And then finally, there's mechanically stabilized earth walls, which are always done in a fill orientation. Even if it's in a cut section, these are fill walls, and there's a temporary excavation behind them, and you're fill up behind the wall. On the cut wall side, there are a whole bunch of non-gravity retaining walls, and we're going to talk about all of these during the course of the course. Well, we're going to talk about all of them. We are not going to get to the design of soil nail walls. But sheet pile walls is a classic cut wall system where the sheet piles are driven first, and then we excavate in front of them. Sheet pile walls actually can be in both sides of this chart. They can be fill walls also. And then another system is anchored systems, which are the way they get their support is different. These ones are all cantilevered, and their support comes from being cantilevered. And these are anchored either with tiebacks or dead men. And then finally, there are in situ reinforced systems, which basically consist of soil nail walls and micro pile walls. And those above the line are externally stabilized systems, and those below the line are internally stabilized systems. So this is just the previous chart organized a different way. So there's basically, I guess there's three really important parameters when you're talking about, there's probably more than three, but if you're talking about systems, one, is it internally or an externally stabilized system? Is it a system that's really designed to be used this really has to do with construction methods. And the construction methods, is it designed to be used with a cut wall construction, or is it with fill wall construction? And then the third one is, what is the nature of the support? How is the structural support for the wall generated? So what we're going to do now is just go through these systems fairly briefly. So the intent of this is not to give you a complete understanding of these, but an overview. Again, I discussed this earlier today. We can either go through system by system and then kind of summarize them at the end. I've decided it's better to go through them in kind of a quick overview fashion now, and then we're going to get into details later. I'm providing you two, I think, really important practical pieces of information from these, and these come direct from the FHWA manual. By the way, this should by now you should have figured out that what I'm producing for you guys for the note-taking aids is a set of slides that have some information missing on it, which gives you an opportunity to write in during class. The intent is to give you something to do other than chew on the end of your pencil or fall asleep. And it may or may not work. That's up to you how you use it. But the two pieces of information I'll be giving you is in general, these are very broad statements, but what are cost-effective heights of these? In other words, at what point these walls are the way, because of the construction methods, they fit in different categories in terms of what heights they're cost-effective for. And then another important one is, this is ROW, if you're not a transportation person, that stands for right-of-way, which is how much area behind the wall is required for you to construct the wall. So, for instance, in a mass concrete wall, you've got to have somewhere between 50 to 75% of the height of the wall. You've got to open behind it in order to allow you to do the construction of the wall. So this is probably not the wall system you want to put in right next to the foundation of an adjacent building when you're going down 40 feet for an open excavation, because you probably would run out of space. So that's the kind of basic information I'll provide you. And then I've got pictures. You can't see that for crap, can you? All right, I'm going to try an experiment here, because I know if I... I have no idea how this is going to work, but we'll give it a shot. Since we have this antique thing here, if the bulbs are working. Well, that's not too bad, is it? Can you guys take notes? Still take notes? All right. Let's hear it for low tech. All right, so this is a really good example of a seldom constructed wall anymore. This is a gravity wall. This is not a cantilever gravity wall, but this is a complete gravity wall. And you can see there, in this case, the wall is made out of quite large boulders. I think I have just one photograph of this. Yeah, I cut down my photographs because the presentation was really long. So in this case, these are very large and massive. If you can see the construction of this, it's quite a big wall here. They've got to be massive because it's the gravity, the shear strength within the wall itself, the boulders stacked up, they're actually providing both the structural support to the wall and the gravity support to resist sliding from behind it. So this is a pretty unusual system to be constructed today. You see them generally constructed at only very low walls, I would say a few meters, and in places where the aesthetics of them are pretty interesting. They're actually fairly high labor intensive, so they're also not used in countries with high labor costs very much. I'll show you how if we wanted a nice rock-looking wall, we do something different in this country. The second type of gravity wall, again, this is the one I discussed earlier. We're not covering this class because it's covered in a different class, are concrete cantilevered walls. There's two different varieties of these. There's actually three different varieties. The typical cantilevered wall only has two structural elements. It has the footing and it has the stem. If the walls, and notice that these are constructed, generally these 2 to 9 meters is the cost-effective range. They take, by the way, one of the disadvantages of these walls is the amount of space they take behind them, but I'll show you in a minute, they take less space behind them than mechanically stabilized earth walls. If you get to higher heights, like up into this range, then structurally you can't build the stem thick enough. Well, you can build the stem thick enough, but if you build the stem thick enough to take the bending and shear generated behind the wall, it's really inefficient. So you end up putting these counterforts in. There's two versions of this. There's one called a counterfort, and this is based, in this case, it's a tension member. And I'll show you photographs of these in just a second. You can flip the wall around and put the counterfort on this side, in which case it's called, boy, I just had brain failure. Buttress wall. And in that case, that element is in compression instead of tension. The buttress, this is a buttress wall. We don't generally use buttresses because all that space in front of it is useless now, even though these ribs are spaced only every so often longitudinally. All that space in front of it's wasted because you can't put a building there. I guess you can park cars between the buttresses or something. So it's not really common, but it is done some. And this, the counterfort wall, the buttress wall, used to be the way we built really high retaining walls, but they're quite expensive, and we have better systems now to do that. So this is an example of a traditional concrete retaining cantilever concrete retaining wall. Here, I like this picture because it's got it in all stages of construction. Here's a completed section of the wall, and a section that is formed up, and the section where you can see the rebar in it. And here's a longitudinal cross-section down there at the bottom of it. You'll see that there's drainage, there's weep holes that provide drainage through the wall so you don't get water pressures behind the wall. This wall is actually designed to flexure both directions because it's a water conveyance, and it's designed so that if you happen to get a big flood during construction, the walls don't fail, so you actually see reinforcement on both sides of it, so it's kind of an unusual wall. Here's a picture of counterforts. So here are the ribs that I was discussing. You notice that they're just placed every so often. In this case, this one's precast. In fact, almost all the counterforts I see today are precast because they're really expensive to form up in the field, and there are cheaper systems out now for them. And this one, these are really big counterfort walls. I'll let you look there for scale. Can you see this right here? That's a human being. So this thing is like, this thing's like 10 meters wide. This is for a marine. You kind of get a better picture of it here. Here's the tractor for the trailer that's going to move this thing around the port. This is for a port in the Middle East, and they're casting. You can see the fabrication facility here. Here's all their formwork for casting these things. So they weren't moving them, but they were casting them right there on site and then moving them out to where they're going to place the wall. So these things can be really big, but the only times they're cost effective is where you can, I think these days is where you can do the precast, because it's really too expensive to do it another way. In this case, there was obviously some economies of scale for putting it. And basically, this is the entire wall, one chunk at a time. You just place it. They placed it on top of a sand fill at the bottom of the harbor, and then backfill behind it. But when you get to really tall walls, reinforced concrete walls, you need to go to counterforts or buttresses. So that's not a real common wall type. So the next category that we talked about were prefabricated systems for gravity walls. A very, very common one. Not so common in this country anymore, but boy, it's really common in Central America, South America, and it's also really common in Australia and New Zealand for some reason. Are crib walls. And crib walls, generally they're made out of concrete now, although you will see them made out of timber. The timber ones tend to be lower. And the relatively low walls, the effective height maybe up to 11 meters. That's kind of pushing it. I would say these are used for most commonly from maybe 2 to 5 meters. Still requires quite a bit of right-of-way behind it. This is a really good example of the construction method. So here, starting from left and going from the upper left corner and going in a clockwise fashion. Here, this is a cut. This is a cut geometry, but they're building this fill wall in front of it. So they've cut back and done a temporary excavation back behind where the wall goes, and then these are pre-stressed precast concrete elements, and there's two sets of pieces. There's pieces that go longitudinally along the wall, and there's pieces that go back into the wall. These ones, these are called stringers. And these ones that go back in here are called stretchers for some reason. I need to change colors, don't I? This is a stringer. This one's called a stretcher. And one of the things that's nice about these is that these things are relatively easy to move around. There's something you can pick up with a backhoe. You don't need a big crane to pick them up. They're prefabricated, so you can truck them on site. It doesn't take a lot of heavy equipment on the site to actually do the construction. You can pick up the elements pretty easily with like I say, with a backhoe and with 2 men handling it to do the placement. So they're relatively inexpensive to install, low tech. They're nicely freely draining if you look at them. In fact, you have to put very coarse fill in it, because if you can see, it's actually open between the space between the stringers is actually open. So you've got to put some fairly coarse material, or else it'll all just erode out of there. You can put vegetation in there, so vegetation will grow over the front of it to give it a less industrial look. It's a real common system to use in alpine areas where it's difficult to get material to there, and it's hard to do casting in place methods and stuff like that. Very common in alpine areas. Another less common one these days, used to be really, really common, are bin walls. In this case, you've got some great big bin. The most common ones are precast. There are concrete ones, but by far the most common ones are precast out of sheet metal. So this is a really good example of a precast bin wall. You basically build these big bins. They're made out of corrugated material. Some of these corrugated materials come in fairly small sections, maybe about that large, where they're small that actually a person can handle them or two people can handle them and put them in. You've got some kind of forms that they slide down into, and you have these bins, and you basically then backfill the bins themselves with really high quality material, with gravel type material, so it's freely draining. These can be pretty, they're again used much like the crib walls because they're pretty low tech in terms of the equipment that's required to do them. Again, you can do it with a few people in the backhoe if they're not too tall. So they're very common in more remote areas like this where you don't want to mobilize a big construction setup. But they can be fairly large. This is an example of one that's undergone some significant structural failure issues here due to probably poor quality backfill or poor drainage conditions. You can see the deformation that's occurred there. But that's a fairly tall wall. It's in Northern California. These are now not so common anymore. I think just because the steel's expensive and the other systems that are available are just as good. Another system is still very, very common. It's particularly common, again, where labor's cheap and low-tech construction is a good thing. You see these all over Central and South America. These are Gabions. A little lower than some of the other prefab systems. Still, again, generally take about somewhere between 1/2 to 7/10 of the height right away behind the wall. So the term Gabion, there's a little history. So these are Gabions here. So in the 17th century, if you were an artillery guy in Central Europe, fighting over land, and you wanted to hide behind something, they'd make these wicker baskets, and you'd fill the wicker baskets full of soil, and it was a nice thing to hide behind, so the guys with muskets didn't shoot you while you were trying to bomb them with artillery. And it's a French term. I'm not sure the real etymology of the French word, but those were Gabions are. So they basically were baskets filled with gravel or soil. So this is our modern version of that. They're steel wire mesh baskets. They sort of look like chicken wire. They're much stronger than chicken wire. And they're galvanized wire that has a significant life. And then they're filled with very select material. In some cases, they're actually filled with hand-placed material in them, so they have they aesthetically look pretty nice, at least if you're some distance away from them. And they are very commonly used in this situation like this, where there's a retaining system around water, because they're highly resistant to erosion as long as you have the foundation deep enough that you don't have scour problems. And they're freely draining because they're filled with very coarse grained material. Let's see. Let me see where I'm at here. I think I'll get through this system and then. So mechanically stabilized earth walls. So mechanically stabilized earth walls, as we said, consist of the thing that makes them distinctive from these other systems is they have these reinforcing elements that go back into the soil, as you see in both these drawings. And so this whole mass of soil back here acts as a reinforced material. In the terms we use for this is the reinforced soil, and this behind that is what they call the retained soil. So all this material behind here is retained soil. So it's obviously material that the wall is holding up, but there's no reinforcement. But that section that is reinforced we call reinforced soil, and we have to worry about we actually have to worry about the design of this reinforced soil, much like you have to worry about the design of a reinforced concrete beam. You've got to design that reinforced section. And the facing material on these, the facing panels, a bunch of different facing materials that come on these. These are modular concrete block walls. The facing material has only two purposes. One is aesthetics, and the second one is to prevent raveling at the face. So it prevents it prevents erosion and raveling at the face, and it has a nice aesthetic look. It is not holding up the soil behind it. The only soil that's being held up by the only soil that's being held up by the facing material is just a little bit of soil right behind each one. So it's just holding up the material right behind it. The bulk of the material back here is being held up by the reinforcement in it. So the facing is not really a structural element of the wall. That's one of the key distinctions. Here's one of the big disadvantages of mechanically stabilized earth walls, and why you still see a lot of cantilevered concrete walls, because it requires a lot of space behind them. In general, this length here is about 0.7 times h. The width of the reinforced area is about 7/10 of the height. Obviously, something you need to design, but it's a good rule of thumb. And you need more space than that behind it to actually do the constructions. So these actually are for one of the built wall systems, are ones that require the most space behind it to be constructed. So there are a lot of cases where this doesn't work. And another issue with these is this requires, notice this says granular soil backfill. There's some controversy about this, because some people contend that you can build mechanically stabilized earth walls with poor quality backfill, with clay backfill, which should be perfectly possible if you design it correctly. But in general, most agencies don't let you do that. And a really good example is the wall at 7th and Sunset. If you drive along Valley, there's a place. If you're driving down Valley and you hit 7th Street, which is also Sunset, on one side it's Sunset, and one side is 7th, kind of near the what's that electronics store down there off of the 60? Yeah, kind of near Fry's. If you've been on the 60, there's a place where the railroad flies over. You know, they did a whole bunch of graded separations there, and there was one place where they flew the railroad over 7th Street or Sunset, which is really unusual. And if you look at that, there's two back-to-back concrete, reinforced concrete cantilevered walls, and they actually have a tie-back rod between the two of them. So it's right. The final design for that looks like this. You've got two back-to-back concrete walls with a tie bar between them, and this is filled, and then your railroad tracks right here. The original design for that was a mechanically stabilized earth wall, back-to-back mechanically stabilized earth walls, very, very common design. But the soils in that whole area are really silty, kind of clay silts. They're not very plastic, but very poor draining material and a relatively low friction angle. And the specifications for the wall, for the mechanically stabilized earth wall, required such quality, the fill quality, the local material they had there that they were going to be in Excavate and other parts of the construction, didn't meet the specifications, and the cost to import the high quality gravel fill was higher than the cost to switch from mechanically stabilized earth one to the actually cast in place concrete wall. And since they've got a tie rod between them, that substantially reduces the moments in the walls, so the sections are thinner. But they actually end up doing two back-to-back reinforced concrete walls rather than a mechanically stabilized earth wall, where in most cases you might think it. And that was because of the cost of the backfill material. So there's the two real drawbacks to mechanically stabilized earth walls. One being this right-of-way requirement, and the second one, the quality of fill that's required. So here's a nice series on the construction of a mechanically stabilized earth wall. So here you can see the placement of the initial layer of reinforced soil, and immediately, what do you notice about the difference between the native soil, the native soil, and that soil that's going in the reinforced soil section? Notice that those are, just you look at the color, they're very different. The one is basically a crushed stone gravel, and the other one you can see obviously has quite a bit of fines in it. So that this gray stuff is expensive, this is cheap. In the second picture you can see, if you look here, you can see there's been several lifts of the reinforced soil. And in this section, this right here is the reinforcement piece. In this case, they're using a non-woven geotextile for the reinforcement. So this is the layer of the reinforcements in place. So you can see this next fill layer is going on top of that. Here's a detail of how they do this. On the face of it, this has the reinforcement's a geogrid. It has a combination of geotextile, which is designed to keep the material bound in there. And if you can see this is a geogrid. This is what they call a wrapped wall face. where the geogrid basically comes up and comes around and goes back down. And so this is a geogrid wall with geotextile right behind it to prevent erosion within the face. And this isn't exactly the same wall, but this is a similar system and what it looks like lift by lift after it's constructed. So in between each one of these lifts, there's a reinforcement layer like that. The facing on these walls can be is very versatile. So this is a wall on one of the roads into Yosemite. It's a mechanically stabilized earth wall. In this case, the stuff that looks kind of like Gabions in the front is just it's just an L-shaped. It's a little L-shaped wire. Change colors again. It's a little L-shaped long wire with a little tension member in there, and that's just designed to keep the face clear, and then behind that is where the reinforcement goes. So that's the wall after they finish the construction of the wall, but this is what it looks like when they finish the final construction. So they did a shotcrete finish on it, did all this nice carving to make it look, aesthetically pleasing near the national park. So this is what we do in this country if we want those nice, stone-looking things. We just use shotcrete and pay somebody to form it because that's cheaper than paying somebody to stack boulders around. So you can see that's one finished face you can get on a mechanically stabilized earth wall. This is a really, really common one, a modular block wall. Very, very common. In fact, you can go down to Home Depot and buy these off the shelf at Home Depot and build yourself a little 3-foot retaining wall at your house without any reinforcement. Very common system. This is a proprietary system called reinforced earth. If you say it's reinforced earth, that's a trademark name, trademarked by the guy who originally developed this system. We'll talk more about that when we get into design. But in this case, the soil reinforcement are metal strips rather than polymer sheets or geogrids. They're metal strips. And the facing material are these are called the cruciform sections because these are each kind of shaped like a plus or a cross. So the next one of these concrete elements will fit in here like this, and it'll come up like this and fit right down in here and have this cruciform shape. And so that each one is exactly the same. They can stack them in between them, and you can see they have little tangs on the back of them where they can attach the reinforcement. And again, if you look at this backfill material, obviously a very high quality backfill material. Wire mesh, welded wire mesh is another common reinforcing material. This is in this case the facing material are full height precast slabs. So these are sort of like a concrete tilt-up wall. They precast the wall face itself, and they tilt it up and put it in place. And then as they backfill behind it, they put these reinforcement layers in, and they're attached to the wall at these little attachment points. And finally, just to show you how complicated it can get, this is a reinforced earth abutment wall for an overpass. In this case, these piles here are the actual structural element that's going to support the bridge, the footing for the bridge abutment itself. And notice that the reinforcing is going in many directions here because you've got side walls that need to be reinforced as well as the front wall and the backfill material. So this is actually being built around these piles. The piles were placed first, and they're actually building the retaining wall around the piles. So it's a really versatile system, very, very popular. If you have the space for the right-of-way and you can afford the quality backfill materials, this is one of the most cost-effective retaining wall systems out there right now. And that is a good time for a break. Okay, so now we're going to move into a different set of systems. And these systems we're going to talk about now can be used both for cut wall and fill wall for the soldier pile systems, although normally they're done for cut wall. So we're moving into kind of a different set of systems. So this first one is the soldier pile and lagging wall. It's a very, very common system that's used in a cut situation. And they call them soldier piles because you put a bunch of these things in, and when you got them put in, they look like a bunch of soldiers standing up next to each other. So that's where the term comes from. So these are usually, not always, but these are most commonly H sections. So for my structure guys, what's the difference between an H section and a W section? Which one's bigger? The web is as thick as the flange. So if you're talking about bending, there seems to be a lot of wasted steel there. But if you're driving them into the ground, they tend to not split at the webs, so it makes the webs are stronger. They are made with W sections now, but most commonly they're done with H sections. So those are the soldiers, and the stuff in between is the lagging. If you can't read that, it's the lagging. You can use both concrete lagging or timber lagging. If you want to see some concrete lagging, go down here real nearby where the 71 crosses over the railroad here, just by Pomona Boulevard, and you can drive down there right now. You'll see some permanent walls. It's a fairly short wall. It's a cantilevered wall, and the free height of the wall is probably only 2 meters. But they put concrete lagging there. It's kind of unusual to do concrete lagging. More common around here to do timber lagging. These things can get very high if you anchor them. With cantilevered, 5 meters is about 15 to 20 feet is about the limit that you can do these cantilevered realistically. But if you're gonna do some kind of an anchored system, these things could get very, 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 very tall. And since it's a cut wall system, you need no right of way behind it. If you are going to put anchors, tiebacks in for your anchorage system, you will need easements to put those in. We'll talk more about that when we talk about tiebacks. So this is the construction method for that. The first thing you do is you place the H-piles. They used to be driven quite a bit, and these days people don't drive them. They tend to drill them and place them in open holes. Drilling methods are a lot better and cheaper and faster than they used to be. And two, the quality control you get by doing that compared to driving a pile is better. It used to be when you drove them, you didn't really know where they went, and when you went to do the excavation, they weren't where you thought they were. So here you can see an H-pile being placed in a hole, and obviously you can see the auger that made the hole. And here's another of the soldier piles here, and there's a whole series of them down the line. Here's a set that have been a different job, but they've been cast in place already. And usually backfill with some kind of a lean concrete mixture, because you're going to have to actually chip that stuff out. I'll show you in a minute why you're going to have to remove that stuff, so you don't want strong concrete. You just want something in there that'll hold the pile straight and hold the soil, keep the soil from caving around the pile. So this is getting ready to do the cut part of the wall. So these have been drilled and placed in the ground, and they're about to actually start the wall construction. So here's a job some ways down in construction. So as you're going down, you excavate down, and you can't see the above this, but someplace right above here, there's some lagging. And they've excavated down below the height of the previous lagging, and they're putting their lagging in place here. And here they're slipping it behind the flange of the H-pile, so they have to actually excavate back in. And you can see this lean concrete fill here that was in the hole. So you can only do this in a material. You can't do this in a clean sand because it won't hold up. You got to do this in some material that has some apparent cohesion, or what they call stand-up time, so that you can actually excavate below the supported area and put the lagging in. In this case, the lagging is just held in there by they just pound a nail into the lagging and then bend it around the edge, and it just needs to be held in place until the soil behind it pushes against it. So this is partway through the construction. This may be the full height of this wall. I'm not familiar with this wall. They just had pictures I could pull. So this is a cantilever type wall, and you can see what the final, I'm presuming this is the final wall height in this one, but I don't really know. And so you have all the soldier piles lined up and in between the lagging. Very common system. This is a different application, obviously a much deeper one. So this one is 20, 25 meters. And here, if you look carefully, you can see these little spots all along here. Those are anchors that are actually going back, or tiebacks, I'm sorry, that are actually going back behind the wall and are grouted back in place. We'll talk about into the quarter, we'll talk about tieback design. So this is a very, very common system. You see this all over, LA. It provides a nice open excavation to work in. And if you do that kind of system, obviously you can get the system very, very deep. And notice that they're excavating, right next. This is an existing structure, so they're excavating right up against this existing structure, and right behind this is street that's actively in use with utilities in it. So this is being done right up against the actively used areas. Sheet pile is another method for doing this. This can be used in a cut or a fill situation. It's more commonly used in a cut situation, but not always. I'll show you a classic fill situation for it. Because the sheet piles don't have as much flexural strength as the H piles, you can't get quite as high an unsupported section with these. These also tend to be really expensive because there's a lot of steel in them, and steel's expensive. You don't need any right-of-way, but you do need will need easements if there's tiebacks. If it is an anchored system, you can get quite deep again. I have never seen concrete sheet pile place, although I'm told it exists and is still used in a few places. The most common type is a steel sheet pile. And when we get to sheet piles, we'll talk more about, there's two basic varieties. There's cold form and hot form, hot rolled sections. We'll talk about those more when we get to sheet piles. They have a little connection system here. There's a bunch of different proprietary connection systems where these things can slide between each other. And so one of the systems is a little basic C-section where that looks like your two hands opposed to each other, and they just so one of the systems kind of looks like this, and there's a mirrored system on the other side. So these things can slide up and down. There's another one that's kind of a ball and pin method where you've got on the one side has kind of a C-shaped, and the other one has this kind of post on the other side that slide between each other. It's used a lot in marine and near marine environments. This is I put this in because it's a picture of a fairly small sheet pile wall installation, but it shows you how the installation works. This is a vibratory hammer, very common way to install them, particularly if you're installing them in soft to medium soils. And you can see there's that little interlock right here. So this pile is partially in place, and this one's being driven down, and they're interlocked there so that they're sliding. The one is sliding down right next to the other one, and then they'll come back and drive this one down. And there's one in between that's already driven, and so you drive them kind of alternately. And when you're done with it, they look like this. They generally there are flat-shaped ones, but you generally end with a Z or a W-shaped section, and that obviously gives you bending strength in the section as a whole, from the different elements that are put together. This is a much larger size job, and you can see a much larger vibratory hammer. This is a pretty old picture, but in fact, this one they're driving flat sheet piles for a cofferdam. Occasionally, you'll see them driven with diesel hammers, although that's not very common. Not because you can't do it, but because you don't need to do it usually, and the diesel hammers are a lot more expensive to operate than the vibratory hammers. Plus, with the vibratory hammers, you can remove them if it's a temporary excavation, and you can't remove them with a diesel hammer. So, but it is done, but only with very thick sections. So it would have to be someplace where you've got really hard driving with diesel, and you've got really hard driving, you're probably better off with a better wall system, but it's done occasionally. So here's an example of a wall that's probably a combination of cut and fill, but notice this one has tiebacks at the top, so here's a tieback sheet pile wall. And if you're in the right locations, that might be aesthetically pleasing. Other places it wouldn't be. This is a very, very common use, a fill use, and we're going to design this type of wall, what's called a anchored sheet pile wall. And you'll see there's a whaler running across here. For those of you who don't know that term, this is a whale. A whale or a whaler. Sometimes there's an R on the end of it. It's basically a beam that acts in a horizontal direction to hold the wall up, and you can see in between. You can see here occasionally. You can see some kind of a round thing here. These are tie rods that go back in this direction, and there's what's referred to as a dead man back here, which is usually just sometimes it's another sheet pile walls, or it could be just a big block of concrete that's back behind the zone that could fail, and that actually tied. It's not a tieback wall, it's an anchored wall, because tiebacks are drilled back into in situ material, and this is not in situ material, this is placed behind her, and then it's filled up behind her. This is really, really common. And in some places where you have really light construction now, you can get polymer sheet piles. They're made of HDPE. So they have very, very low strength, but if you have very low heights, they're very, very durable, and they're used in some marine environments now. I've seen them in a few places. So this is a very, very common wall, and as you can see here, you generally fill behind it, and then you can come and dredge in front of it and get nice, clear heights for waterborne vehicle traffic. So I'm going to move on now and talk about excavation support. As if you remember, we talked about excavation support being a very different type of design system. So I'm going to go through the process, the construction process, to give you an idea how that's done. So excavation support is where we're trying to open a hole in the ground next to something. We can't. The quarters are tight enough, or the excavation we need to make is deep enough that we can't just do a temporary slope. So this is very, very common in urban environments around in Southern California, the places where you're trying to build a new building, 6 inches from the building next door, or even 12 feet from the building next door, and you can't afford to do any kind of a cutback. So that's the classic use for excavation support. The very first thing that you do in excavation support is you install the wall element. So here's the wall element, just generically some structural element that's installed in the ground. Before you do any excavation, you install this element. So we've already talked about some of these. These elements could be soldier piles, in which case the installation method could be either you drive the soldier piles or you drill a hole in the ground and drop them in and grout them in. They could be sheet pile walls, so you could take sheet pile walls, use a vibratory hammer and place them in the ground. You haven't done any excavation, you just end up with sheet pile in the ground. We'll talk more about diaphragm walls in a minute, and secant and tangent pile walls. These are all different methods. And then there's a method called soil mixing, which we'll talk about very briefly. But you install this structural wall element before you've actually done any excavation. So that's the first step. The second step then is that you actually start excavating and the side of the wall that you want the excavation. So generally you excavate down. These systems are almost always supported with some kind of lateral structural elements. So you excavate down to the first level of support that you need, and then you install the support. If you're putting tiebacks in, you're going to drill down at an angle and put in some kind of you're going to grout this system back here. We'll talk later about how that's done, but provide a tension system that's attached here. If you're putting in a braced excavation, then you put in a structural element horizontally in here that's somehow attached. If this is a excavation that's got two sides to it, the brace can go all the way across. You can actually put in an angled brace if you want to. It's called a raker. But the basic methods are tiebacks or bracing. So that is two things for you. It provides lateral support to hold up the soil behind the wall. It also reduces the bending moments in the wall because you're providing basically reaction points along the height of the wall. And then you excavate down to your next level. Put your next level of support in, excavate down to the next level, and this is excavate down to the bottom. If you're going further, you might excavate farther down. If you've got anchors in, it would look like that. If you've got bracing in, it'll go across the structure. So that's the basic construction sequence for excavation support. So I want to talk a little bit, though. We've already talked about two of the wall elements. We talked about soldier piles and lagging. We talked about how that goes. And we talked about sheet piles. And there's two other wall types that are of the wall elements that are very, very common. One's diaphragm walls, also called slurry walls. Although the term slurry wall is now, these used to be called slurry walls. When people say slurry walls now, they're usually talking about a hydraulic barrier and not a structural barrier. So you'll still hear in older literature, you'll hear these called slurry walls. But today when you say this is usually a bentonite hydraulic barrier, which is something very different than a retaining wall. So if you're reading old literature, you'll hear the term slurry wall discussing a structural wall, but if you hear it today, they're talking about a hydraulic barrier. So this is what diaphragms or slurry walls look like. You're basically installing a reinforced concrete panel in the ground. There's two systems. This older system is not used very often because the steel's expensive, but you can use H-piles or W-sec. You can use, these are either H or W sections. You can use either H or W sections to provide the flexural support for the wall with concrete in between, or more commonly, you're actually going to use reinforcing cage to do it. And so you're going to install this in the ground before you excavate. So somehow you got to open up a rectangular hole in the ground, fill it full of concrete, and get a reinforcing element in there, which sounds pretty interesting, doesn't it? So this is how this is done. The first step is to build what's called a guide wall, which is a small structure at the ground surface that's going to guide your excavation equipment to assure that you have the walls in the right place and initially starts going down nice and vertically. So here's the construction of a guide wall. You can see this is where the wall is actually going to start, and they're actually placing, if you can see here carefully, there's some rebar in here. They're placing a little small L-shaped concrete structure that's going to guide the excavation equipment, and that'll be outside the edges of the diaphragm wall. Then, in between those guides, you start excavating a big rectangular panel. So this top part is an elevation view, and this is a plan view down here. So you're within that guide wall. So your guide wall would actually be placed in this plan view right along here. You're going to go down in between there, and somehow you're going to excavate a slot in the ground. You do this under slurry. You got a bentonite slurry or a polymer slurry in there to provide the support to keep your hole open while you're excavating down. And there's two methods. There's two pieces of equipment that you can use to do that. One is it's a rectangular shaped clamshell type bucket, and it goes down the bottom, and it's just a clamshell bucket, except it's got a rectangular cross section. And you're going to excavate this thing in panels. I'll show you the other system is a rotary system, where there's some kind of a cutting device at the bottom that cuts the soil out, and you pump the slurry up from the bottom, very much like a rotary wash boring. This one works better in sandy soils. The other one works better in more cohesive soils. But they both work and can be used in both. And so this one depends on the circulation of fluid to remove the cuttings. So those are the two. There's a bunch of different designs for these, but those are the two basic styles. And at the end of each panel, you got to put some kind of a stop in here, which is like a temporary tube or something that you're going to use to form the end of it, so that when you put the next panel, it's connected to that one. And that's actually a pretty important design detail, and we'll talk about that when we get to the design of these things. So now what you've got is you've excavated this nice rectangular slot in the ground, and it's filled full of mud. So if you looked in cross section, this is what you in the cross section view. You got your guide walls along the sides, and you got this big hole in the ground or this rectangular hole in the ground that's filled with drilling mud. So now you got to. I haven't seen one of these done with H-piles. I haven't personally ever seen one done, and mostly now they're done with rebars. These can be pretty big structures of themselves. You can see this one being picked up. I think there's a 3-crane pick with this. When I looked at this job, they took 3 cranes to pick this up, because obviously you're going to build this huge rebar cage is actually built, sideways on the ground like this, and then some, which is not actually an easy way to pick it up. It's not designed to hold its own support. So in some cases, some of the critical designs of the rebar cage are actually making it strong enough that you can pick the thing up. Anyway, you pick it up. Once you get it vertical, it's pretty easy to put in there. You'll see some interesting things in here, like you see these things that look like tubes up here. Can you see those? Those are tubes. Those are actually where the anchors are going to go in this system. They're actually holes. They're going to be holes in the wall where the anchor system is going to go. So you pick that up, you drop it down in the slurry. So now you've got your panel, and you've got your reinforcement cage in the slurry, and that's why you need this end stop here, so you got something to put it up against. And now you fill it full of concrete. You have to trimmy it up from the bottom. So trimmy is just a word for a funnel with a really long chute at the end of it. And really, it's just a big metal tube with a funnel on the top of it. And you trim it up from the bottom, and the concrete then displaces the drilling fluid, and so you have to have a way to pull the drilling fluid out there and recycle it. And you just fill it up, and then when you're done, you have a panel. And you basically, kind of like we saw that cantilevered retaining wall being constructed, you construct this in panels. So you go in here and you put, well, there's two ways to do it. There's a way to do it in alternating panels, where you excavate this one, you excavate this one, and you cast them, and then you come back and excavate this one in between. So that's that sort of hopscotch method. Another one is you place this panel and you let it cure, and then you come and excavate this panel and you place it and let it cure and do the next one. The advantage of the hopscotch method is you can be doing two panels at the same time. You don't have to wait for one to cure to do the next one. And obviously you could do this out in both directions from a starting panel, so you could be working at two sides from that way too. But it's done a panel at a time. So here's an example of a completed diaphragm wall in Chicago. This is, I think, at the Field Museum in Chicago. And if you look real carefully, this is not a real high quality photograph, but if you look real carefully, you can see a bunch of dots there in that wall. Can you see the little dots in the wall? Those are anchors that are going back. Those are it's a tie-back anchor system. So secant piles and tangent piles. So secant piles and tangent piles are where we're going to use a drill rig to make a hole in the ground. We're going to fill it full of concrete and some kind of structural elements, and we're going to put them right next to each other, either very, very close to each other or intersecting one another. If they're just touching each other, then that's a tangent pile because the tangents are touching. And if they actually intersect each other, you know, and there's a secant that's cut off there, they're called secant piles. The reinforcement can either be a H or a W section, or you can reinforce it with a reinforcing cage as you would a drilled shaft foundation. So this is the construction sequence for either one of these, whether they're secant piles or tangent piles, is you drill every other hole. So these are usually called the primary shafts. You drill them first, and then you come back in between and drill secondary shafts. And if they're secant piles, obviously you have to have a concrete strength and a drilling capacity to allow you to drill out that concrete you just placed. So there's a bunch of different categories of these based on whether you have they call them firm or firm hard or hard, depending on whether the strength of the concrete in the two ones. So firm means you have two different kind of soft concretes, and firm and hard means you have a softer concrete here and a hard concrete there. And this just talks about notice that these ones, they're about the same strength, and these ones, there's a lower strength one here and a higher strength one there. Or you can put ones where they're both hard, but you have to have better drilling equipment to do that. So here's a really good instructive picture of how these are done. You need to have you don't have a guide wall in this case, you got some kind of guide tube. It's pretty important that you get these started off drilled in the right direction, because if your drill starts wandering around and you get down there and they're not connected once you get down, that's a bad thing when you start the excavation. So you spend a fair amount of time at the top forming up a system to allow you to the equivalent of a guide wall are called guide tubes. And here you can see it's a secant wall construction, because you can see how they're going to intersect there. There's actually a fair amount of construction here to place these things. And notice they've got them filled full of soil here. You can't just go start placing concrete around these sonotubes without filled soil. They'll start moving around. So they actually place all these sonotubes, they slot them so they can put them in the way the secant piles get in. They fill them full of sand, and then they start filling concrete on both sides of them carefully so they don't shift around, because you don't want them to move. In this case, they're excavating a shaft for where they're going to put. I think this was for a actual jacked pipe construction, but they're doing a shaft down to. Anyway, it's a shaft down to some kind of horizontal construction. And then you start drilling. If you can go without casing, you can just drill them uncased, but lots of times this is done in soils and gravels and sands that require casing. So here they're installing the casing. They're actually vibrating the casing in this case. So they vibrate the casing in place. It's a combination of vibration and rotation. And then they clean it out. In this case, they drill inside the casing. If you have materials, and you can look at, if you see the material the spoil come off there, you see it's pretty granular, not a lot of cohesion. If you have a very cohesive soil, you can just drill in there and do an open hole method, or do a slurry. You can do it in a slurry method too. And then you backfill. So in the case of a case one, you can just dump it in. If it was a slurried system, then you have to trim it up from the bottom. If it's an open hole system, you can just dump it in. And then you're going to set the beam or the rebar cage. You often don't reinforce every one. Oftentimes they're designed so you only have to reinforce every other one, or sometimes maybe even every third one, but more commonly every other of the piles is reinforced. In this case, once they do that, they've got to pull the casing because this is a case system, so you don't, obviously the casing is pretty expensive. If you're just going to put a bunch of steel piles around there, you could do you wouldn't bother to be pouring concrete in the middle of them. So that, again, it's vibrated out. So this is a fairly complex one where they were using casing. Pretty unusual. Well, I don't know if it's that unusual, but very complex anyway. And here's a really good example of what a completed secant pile wall looks like. So this is a good example of both a secant pile wall and bracing used for this open excavation. And this one's using what's called corner bracings. It's kind of hard to see here, but notice there's two whales in here. There's one whale at the top, and there's another one down here, which they're about to put the bracing in. But if you look carefully, this is the corner of the excavation. So the excavation looks like that. And then these braces go off at 45 degrees. So in this one, at least the center of the excavation's open, and the edges of it are still pretty clogged up by the braces. But those are called corner braces for obvious reasons. Soil mix wall is, soil mixing is where rather than removing the soil and replacing it with concrete, you basically are going to mix a Portland cement or other cementation material, but it's usually Portland cement. It could be Portland cement with fly ash or some kind of other pozzolans. But you mix it with the in situ soils. You're basically making really crappy concrete, but really crappy concrete is usually much stronger than soil. And so it's soil mixing. You're mixing the soil with a cementatious material and letting it harden in place. The process is very, very similar to secant pile construction. Well, there's both individual drill methods and there's also panel methods that actually excavate more like a panel, like I showed you for the secant piles, and do the mixing within more rectangular shaped panels. So here's a method of doing that. Again, you have primary strokes and secondary strokes. So you come in and you'll place this kind of rectangular section, or a place that you'll mix that up, and then mix this one up, and then come in between and do one in between. And some of these methods mix with things that look like augers or paddles, and other ones mix more with that kind of chainsaw kind of thing we saw. It does more of a rectangular shape. Takes quite a bit of equipment to do this. You got to have a grout plant on site because you can't ship. You can't just have your your grout shipped in like you do with the concrete placement, because you got to be able to generate the grout as you do the excavation. So you got a grout plant on place. And this is not a very good picture of this. I'll show you a better picture. But here's the auger rig that's going in, and you've got your grout plant feeding that. This is a better picture of the auger type systems. They're not really augers, but they're rotary systems. So this one has four. It's going to make four of those sort of circular shapes in the ground. They have methods to inject grout in them while they're doing the excavation. So here's a good example of a mixing, and you basically end up with this real messy stuff. It's basically very, very lean concrete. So you definitely want to wear your wellies when you're working on these sites. If you're doing, here's an example where they're going to be using, in this case, a W section of reinforcement. If you're doing that, you need some kind of a guide section to help you place it, because if you realize what's going on here, it's once you get done with this excavation, it's kind of hard to remember where the wall is and where just all the spoil is that came off the top of it. So you need some kind of a guide system to place your reinforcement. So in this case, they've got guide beams poured along the side, sort of like those guide walls, and they're going to put these templates in so they make sure it's placed in exactly the right place. In this case, this is a W section. So that's soil mixing, and you could also be reinforced with a reinforcement cage. But oftentimes this one is done. Oftentimes the reinforcement of this is W or H sections, because it's kind of the soil mix material is really viscous, and it's pretty hard to place a reinforcing cage into it. So lots of times this one is done with structural elements that are W sections or H sections. So we've showed a bunch of different pictures, including ones like this that require a support system to hold the wall up. In this case, it was with bracing, or in a case like this one, where we're using tiebacks. Just want to just briefly cover the support systems. Oops. So tiebacks, there's two kinds of support systems. Tiebacks, which are drilled systems. They're normally cables. They can be bars or cables, but you drill back, as we showed in the previous picture, and you're going to grout these things in place, and they're tension elements that you're going to grout back behind where there could be a failure behind the wall, and then you're going to pull them in tension, and they're tension elements. And the other ones are braces, and bracing are compression elements. There's three kinds of bracings. There's rakers, corner braces, and cross slot braces. And we've looked at a couple of these already, but I'll go over them in detail now. So this is a typical tieback installation. You're going to excavate it down to some point in your wall. You're going to have your facing material in place of some sort or another. You drill back at an angle. These can be fairly steep or fairly shallow. About 10 degrees is about the minimum. The minimum this is going to be greater than about 10 degrees, generally speaking. So you're going to drill a hole back in there, well behind where you're going to put it in. You insert sort of tendon in. A tendon could be a steel bar. More depending on the length as they get longer, they'll be high-strength steel cables or wires. So here they are installing the tendon in there. So the tendon, it just sounds really simple. You can drill a hole around and you're going to stick a steel bar or some wire in there. Well, there's actually a lot of stuff that goes in there. So this is the tendon. The tendon is actually encapsulated in that plastic tube because this is a permanent anchor in that, and everything in that tube is the corrosion protection for the tendon. These white tubes are grout tubes in there that you're actually going to use to pump grout back in the anchor zone. Your wall is going to be anchored. When you get back here, back at the end, it's going to be grouted back for some section here, and then this is going to be grouted, and this section is going to be free. It's not going to be attached to the soil, so you can actually pull it in tension. If you don't have a free section, you can't tension it. So those are the tubes you're actually going to grout with. And then you're actually going to grout your anchor in there. And there's pressure. There's a bunch of different methods for grouting. We'll cover them later. There's gravity grouting, pressure grouting, a bunch of different ways you can grout. There is quite a bit of equipment that's required on ground again, because you're going to have some way to mix the grout and have a system there to do that. So you're going to need water to do that. You're going to need some kind of a cement storage silo, and you're going to have a mixer that mixes up the grout. And then you got to have a pump system that actually pumps the grout in. If you're using pressure grouting system, then you need to have a fairly high pump system. And then once you put the tiebacks in, you're going to tension them. This is actually a jack that's actually temporarily attached to the tendons there, and it's going to pull it out in this direction. And then you're actually going to put some anchors in here where they're actually the permanent anchors are in there. And here they are doing the testing. When you do that, we'll talk about the testing systems that you do for this when we get into the design part of it, but you're actually going to pull these things out to full strength and test them, measure creep and stuff to make sure that you have the strength that you wanted. I guess I've got systems shown in here to do the testing. This is what that anchor system looks like. It's a little wedge-shaped thing, and these are designed specifically for the kind of systems that you're going to install. And so you pull the cables really tight, or the tendons, whatever the tendons are, and you put these little wedge-shaped guys around them. And if you can see real carefully, they're split. They're usually split in threes. They can be split in two pieces, but normally split in three pieces. There's a little O-ring there that holds them together. You slide that in there, and then you release, and you release the tendons a little bit. You have to over-tension them because you're going to release them a little bit, and then the friction just locks them right in there, and that's what it looks like when you're done. If you put in bracing, we're using the same systems as tiebacks, except now we're going to put these compression elements in, and they're actually going to be in the excavated zone that they're interested in. So We talked before about these three types: rakers, corner braces, and cross-lot struts, and the best way to describe those is to show them to you. This is by far the oldest method of excavation support, and I've got a really cool picture of one of the first known pictures of a braced excavation in New York City. And this is, I've forgotten the date. I want to say I think it's 20th century. I think it's 1907 or something like that. I know that, I've got the date written down someplace. I'll have to look it up. Here's one from the 60s. And then this one has corner braces and rakers. So these things are called rakers. So they're angled braces that bear against you pour temporary footing in the ground here or something for them to bear against. These are some of the I want to say the weakest. These are the most flexible of the bracing systems, so they tend to provide the least amount of control in the excavation because you're actually loading soil here. This is an example of corner braces. Corner braces are nice and they can be pretty stiff, but you can only go so far with them. And if you got a really, really wide excavation like this, you can't put braces all the way across it, so you end up with rakers if you're in that kind of system. The alternative to that is the tiebacks that we just looked. So this is from the east side, the Gold Line east side construction from about 7 years ago. It's a really nice example of cross-slot braces and corner braces. So this is a corner brace. You notice these things aren't teeny little structures. These are pretty big structures. And this is a cross-slot brace that's going all the way across in this direction to the other side of the excavation. I think I've got even a better picture of that. Yeah, so this is a really good picture of cross-slot bracing. And so you can see the problem with bracing is your construction site's pretty congested and confined. And you actually have to get all the soil out of here. And to get the soil out of here, you got to come down here with some device and pick it up and pull it out. And you got to do that without knocking out your bracing. So it's really congested in there. So the disadvantage of cross-slot bracing is your construction site gets congested. The advantage is you're not on anybody else's real estate. Where if you're doing tiebacks, you're usually into somebody else's real estate, and you've got to get easements in order to do that. And some people won't let you do that, even if it was in their best interest to do it. I want to very briefly cover soil nailing. So soil nailing, people think sometimes confuse this with anchored walls. It's not anchored walls. It's a way of reinforcing the soil behind here when we can't excavate it and build it up like we do with an MSC wall. So this is closer to an MSC wall than an anchored wall. Really, a lot of the construction techniques are similar to anchors, but it's not an anchored wall. It's closer to an MSC wall. It's an internally stabilized system. And basically what we do is we excavate down, we drill a hole in here, and we put some kind of reinforcing element. There's two ways you can tell this is an anchor. First of all, these elements are not tensioned. Usually they're just bars, single bars, and you just throw them down a hole, and then you grout them, and you grout the entire length of the hole. So these are not anchoring the wall, they're reinforcing the soil behind the wall. It's a different system. They're always angled down because you have to angle them down in order to get the grout to fill from the bottom up. So you don't put them horizontally, otherwise the grout doesn't stay in the hole. But it's not an anchored wall. And they're designed in much more similar fashion to MSC walls than they are anchored systems. So the excavation method is pretty simple. You excavate down as far as you can afford to have it stand up. You place your little grout system in there. And then you place reinforcement on the surface of it. So these ones actually have a reinforcement system on the surface of it, and I'll show you a good picture of that. And then you just keep going down and placing an anchor, going down and placing an anchor from the top down. So this is a really nice picture of it. So here they're doing an excavation of the series of it. So doing an initial excavation into the ground here. This is actually looks like some crappy rock rather than soil. So and then in this picture they've excavated down and placed to some system. Here's the anchor and here's the actual reinforcement. And now they're starting their excavation below the last layer of this wall, and the wall itself is shotcrete. That's almost exclusively shotcrete used with these. So you drill down again, you place your next layer. So here they are drilling the holes for the nails for the next layer. And you can see the shotcrete wall above it, and you can see all the nails placed there. Then they're going to, here's their tendon they're putting in there. And notice this is a single bar, and it has these things that look like little Chinese lanterns. They're called centralizers to hold the bar in the middle of the hole. and then they're going to grout those holes. And notice that here's your finished wall. Notice you got drainage material behind there to provide drainage behind the wall, so you got drainage. And then they just start they place these, they grout them in. I got a picture of the shotcreting someplace. And there's reinforcement elements along here, generally welded wire mesh like that. So it's not a really strong wall face. And there's prefab drains in there. There's your wire mesh. You've got this some kind of an alignment pin or something that shows you how thick the wall is supposed to be. Sometimes they use piano wire stretched across there. And then the guy comes in here and shotcretes along the face of it, and there's a guy behind him kind of finishing it up a little bit. So notice you got this piano wire here that tells them how much shotcrete to put on. And so you just excavate down that way. And that's what it looks like as you go along. It's actually a pretty nice looking system. And here's an example of a completed soil nail wall. These actually can be permanent systems along the 10 here. When you guys when you guys are taking at the 10 and 57 entrance there's that wall that goes up there. That's a soil nail wall. If you're taking the transition from the 10 east to 57 north, that wall along there is a soil nail wall. So on the shotcrete face of it, you can do all kinds of different finishes. So what are the key selections for a wall? The key variables that we need. Well, one is the system geometry. And that's like, what is the right-of-way behind it? Is this is my overall excavation a cut excavation or a fill excavation? What are the performance requirements? Is it a temporary excavation or is it a permanent excavation? Can I allow movement of the wall, or am I building 6 inches from the neighbor's foundation and I can allow little or no movement of the wall? What constructability issues are there? Can I put anchors? Can I put tiebacks in? Can I get permission from whoever owns the real estate behind my wall to put tiebacks in, or can I not? What kind of the soil conditions? Do I have to de-water? There's almost always aesthetic requirements unless you're doing temporary shoring for a construction job. Some people don't want an exposed steel sheet pile wall, and other people think that would be fine. And there's often environmental constraints. Are you going to be placing these walls in places where there's contaminated soils? You got to deal with that. Do you have corrosive conditions? Is that something you've got to worry about? What are the environmental constraints? And the performance requirements, there's a big difference between how we design short-term versus long-term. That's a huge issue. What are the allowable displacements? Is there future construction going to be required? Is this wall going to be is this temporary excavation wall going to actually be part of the permanent wall, the basement wall for the building? Are you going to remove it afterwards? Do your tiebacks have to be removed afterwards, or are they permanent? So there's a lot of issues associated with that. And I just wanted to do, I think people are catching up. Let me give you a second to catch up. I'm running over, so I'm trying to, make up for it by rushing. Like that's helpful. I think I'll just talk to these real quickly so you can come back and look at them. But this is your geometry issue. If you're in a situation where you're in a cut situation where you're actually cutting the ground and you're trying to figure out what kind of wall to put in, if this is your original ground surface and this is the limit of right-of-way that you're allowed to use, you're going to have some safe temporary excavation, and at best it's probably going to be 1-to-1 unless you're excavating in rock. Well, that only allows you so much space here to build your wall. And this is one of the selection methods that you've got that drives your selection. This is this geometry question. If you're in a situation where you're building up from the ground surface, this is not an issue. But if you're in situations where you've got to cut, it's almost always cheaper to do a built wall than a cut wall. But you may or may not be able to have the space behind you to do the temporary excavation so you can do the built wall, the fill wall. So this is the geometry exercise that you've got to do when you're trying to decide what kind of systems to put in a situation where you've got a cut situation but you'd like to do a fill wall versus a cut wall. All right, I got to check to see how far behind I am here. All right. Constructability issues that we got to be concerned about. Is there limited access? What kind of labor is available? You see Gabion walls all over places where labor is cheap, and you don't see Gabion walls in Southern California any place because you can't afford the labor to fill the Gabion walls up. That's not, I want to say any place, but I mean, if you, I go to Guatemala a lot, and I see huge Gabion walls there, and there's no way in the U.S. you could afford the labor to build those Gabion walls. What's the construction season? You know, you have a real limited season you can get in there. Are there environmental concerns with that? What kind of weather concerns do you have? We could go on and on about the constructability issues. Groundwater is a great constructability issue. And then here's some aesthetics. You know, this is a pretty nice looking wall. This is probably not the wall you want next to the Beverly Hills Mall or something, you know. And aesthetics are definitely in the eye of the beholder. And I think this is my last one. I hope this is my last one. I think I covered all these. Oops. Right? Did we talk? I at least mentioned all those. And this is the reference that you're going to want to use for that first. So that I give the first homework problem is the first problem set is just I give you a scenario and I ask you to select methods for these walls. I realize this is a very brief and shotgun overview of wall systems, but it'll give you a chance to at least think about the systems. So the whole point of that exercise is for you to think about it, try and understand what the constraints are and the things that affect wall selection, and with this reference, take your best shot at deciding what kind of wall systems that you would install. And you're not going to do it exactly right because you don't know enough about the wall systems to do it, but this is one of those chicken and egg things. Which one are we going to start with? So we're going to start this way, and you're going to do your crude little effort at it and the best job you can, and by the time you're done with the quarter, you'll be able to come back and do a better job of it. Cool. Well, I'm over time, and I'll quit.